They're somewhat disjointed, and we had both a seminar and a faculty meeting, and I don't mind the seminars, just faculty meetings. The only effect is to pretend that we have some semblance of Athenian democracy, whereas we actually have a dictatorship.
Random dictatorship.
Looking for, I couldn't think of a good adjective for Moscow. Moscowing. All right, anyway, we were talking about, I've been following lately my notes, which are called masses, and I also the notes called spinners. Both are on the website, and I think these are what help us to understand the weak interactions. Now, so we've seen that there are basically two kinds of mass terms. There's the standard Dirac mass term, and that works fine for the quarks and the charged leptons. When it comes to the neutrinos, we don't really know what we're dealing with. We don't know whether we have 3 Majorana neutrinos, 3 Dirac neutrinos, 6 Majorana neutrinos, or more, but it's really somewhat uncertain. We've seen that there are 2 kinds of mass terms. There's the Dirac mass term, and then there's the Majorana mass term, which can work for neutrinos because they have 0 charge, and also have. In the case of the right-handed neutrinos, they have no hypercharge. So they have T3 equal to 0, Y equal to 0, Q equal to 0, everything to 0. They just, well, not interact as far as the standard model goes. On the other hand, we can add them in, and if we add them in, we can have a mass term for these things, which would be nu right transpose sigma 2 nu right. This violates lepton number. On the other hand, the masses here are could be quite small, and so the violation of lepton number wouldn't be very big. Notice that this is Lorentz invariant and gauge invariant. This sigma 2 is a sigma 2 on the, this is a 2-component right-handed spinner. And we've gone through in class why this is Lorentz invariant. It's also gauge invariant because the gauge quantum numbers of nu right are precisely 0. So under gauge transformation, this just sits there in waves at the other fields that have to undergo various contortions. Okay, so so let me, before going on with the neutrinos, let me go back to the covariant derivative. And one way of writing it, and now I'm going to write it this way: d mu plus I e over root 2 sine theta w, w mu plus, and t plus, I should write ckm, but I'm just going to write c for Kabibo. We have to have the k and the m in there, but just to keep the notation a little bit simpler, so I don't run out of chalk. And notice what I can do here is I can say this is the covariant derivative acting on the Lorentz, the Dirac four-spinner, because the T3 of the right-handed quarks are 0. That was one of the things that I was starting my notes with, is that, yeah, for the right-handed quark, T3 is 0, so we don't care. And so we can put it in, we can have these terms, but on the right-handed quarks, they just vanish. And we have I equals Z mu, and this is then T3 over sine theta weak minus sine theta weak Q plus IE mu Q. Now, on the right-handed fields, these terms are just identically 0. The hypercharge has been absorbed with T3 into Q, and so on the right-handed fields, forget about this, you just have this. On the left-handed fields, you've got the whole business. Okay, now remember what this T plus C is 0 and U dagger LD 0, 0, and T minus CKM is 0. Yeah, I'll say it but not write it. Okay. Sorry for the squeaks. Okay. This matrix here, the CKM matrix is often written as V, and it's LU dagger LD. Remember, the LU and the LD were the left-handed parts of the CKM, of the singular value decomposition of the mass matrices, either for the up quarks or the down quarks. So in other words, we had something like M up equals, I guess I called it RU dagger V sigma LU. And a similar MD is the masses of the down quarks, the 3 down quarks, RD sigma LD. And these the R and the U are unitary, so clearly the CKM matrix is unitary. Now, in the original version that I put on the website, I basically left it at this and didn't go on to explain things in a little more detail. But it's useful to go one more step. And the one more step is just to imagine that this covariant derivative is not acting on individual quark fields, but is acting on a sextet of quark fields. In other words, what we're talking about here, we would have something like Q dagger gamma mu d mu Q, where this Q, the Q that I'm going to be talking about, is going to be up, charmed top, down, strange bottom. It's funny, I can remember the names of the quarks better than I can remember the names of my colleagues. I don't know what that means. All right, anyway, let's write this out in a way that I think makes things clearer. It makes things clearer to me. I hope it makes them clearer to you. So I'm going to take that on its, put it on its side. So we're going to have UCT DSB. I'm making, so let's just make clear that we have, this is a new page here. If you want, it's, each of these fields is daggered. Okay. And then we have a matrix, and the matrix here is 0 V dagger W minus mu V W plus mu 0, and then U C T D S B. So that's what this looks like. In other words, if we look at this term here means W mu times this, so it's an LU dagger LD. Well, that's just V. So there's a V here and a V dagger there. So there's the V. So this is 3 by 3. This is the gauge boson. 3 by 3. So this is a 6 by 6 matrix. All right. Notice we can, since we have a V dagger here and a dagger there, we can rewrite this, and we can say that this is the same thing as UCT, and then V acting on DSB. In other words, I'm going to pull this matrix V. This matrix V really only acts on the DSB from the right, and this one really acts on the D dagger, S dagger, B dagger from the left. Okay, just think about it. In other words, it's like that. And so it's, in other words, we can say B dagger, S dagger, B dagger. B dagger is the same thing as V DSB dagger. Okay? All right. And so if I do that, there's the big dagger, and what we have left is just 0 W plus mu times the 3 by 3 identity matrix, W minus mu 0, and then UCT, and then V on DSB. So in other words, what the CKM matrix does is it tells us that when we do the weak interactions on the quarks, we take the mass eigenstates and we take linear combinations of the down quarks, and then everything's fine. And in fact, we can use this same thing, this sort of mixed mass flavor sextet, we can use it in this whole covariant derivative, because on the part that's diagonal, just involving Z and A, we would just have V dagger V, and that would cancel. So in other words, for the purposes of the weak interactions, what we do is we use mass eigenstates, but a funny combination of them, namely UCT V DSB. So this is our sextet for the weak interactions. This 3 by 3 matrix, as I said to you last time, by rearranging the, rebaptizing the quark fields for the phase, we can remove 5 phases. And what that means is that effectively the CKM matrix is real except for one phase. That's a CP violating phase. And so here are the numbers. I'm going to leave out the experimental errors, but you can get some idea of how big they are from the significant figures that I'm writing, which are, I got them off the web this afternoon as opposed to the stuff in Schwartz's book, which is old. 97427. Of course, the place to go for all numbers is the particle data group. So you Google particle data group and then what you want. Oh, and I forgot to look up what the limit is on delta. Somebody who has a nice iPhone or a good connection might go to particle data group CP phase of CKM matrix and maybe tell us, unless you actually know, what the limits on delta are. Notice though that delta multiplies a very small number. 0.97 Okay, so in other words, we make them, if we set delta equal to 0, then the CKM matrix is not simply unitary but real. Since it's unitary and real, it has to be orthogonal. So it's an orthogonal matrix, real orthogonal matrix. So each of the columns has to be orthogonal to the other two columns. Each of the rows is orthogonal to the other two rows. And what we see is that it's almost diagonal, but not really. There are big off-diagonal terms here, namely the 0.22, and you might wonder, how can it be so big as 0.22 if it's 0.97? Because the sum of this squared plus that squared has to be 1 and so forth. Well, the thing is, when you square a fifth, you get a 25th, which is like 0.04. And you square this, you get something so that it all works. This number, in the old days, we only knew about 2 families. In fact, we didn't even know about 2 families. We only knew about 3 quarks, up, down, and strange. And so what we had was something much simpler than this. And all we did was we would say, well, we've got the up quark, and instead of the down quark, we have a linear combination of down plus strange. And in particular, what was the combination of down plus strange? Well, you can see it was basically ds on 0.97, 0.22, 0.22, 0.97. And so it was 0.97d, and then this one was 0.22s. Oh God, I did it wrong, didn't I? So what would happen is that what we would have up quark, and then down here we would have down quark times 0.97 plus 0.22s. This s was called, this was said to be the sine of the Cabibbo angle. So the Cabibbo angle was like 1/5. This was thought to be the cosine of the Cabibbo angle. All right. Do you have a value for delta?
I didn't find it.
All right.
We have
So
this matrix without the...
next week, Thursday. Thursday, I'll try to give you what that is. I don't quite remember. So we, all right, so anything more about this CKM matrix? All right. So let's go on and look at some more things here. I think it's instructive to refer to the notes on spinors. And if we do, what we see is the electron left-handed, the neutrino, the electron neutrino left-handed field is U of P spin down, A1 of P spin down, type nu E plus I A2 P spin down, type electron neutrino, and this is all divided by square root of 2, e to the I px plus an antiparticle spin of dp, the spin up kind, and then A1 dagger, P spin up nu E plus I A2 dagger, P plus nu E root 2 minus I px dqp 2 pi to 3 has. And of course the electron field is same thing except so it's ditto except instead of nu E we have E. Okay. And before symmetry breaking, we have a gauge invariance under which we rotate the neutrino and the electron field into each other. And what that means is that, of course, they're essentially the same, which is, I guess, what I'm representing here with the dittos. In the same in the sense that, well, we're not really the same, because this is P minus type electron plus I into P minus type electron and so forth. So what do we have as states? What we have as states is 1 over root 2, A1 plus P minus nu E. And if we're making creation operators, then we take the adjoint of that, minus I, A2 dagger of P minus nu E on vacuum. These are the, this is one state, and another state is A1 P plus nu E plus I, A2 dagger P plus nu E. Okay, so what do we have here? What we've got is two, for each momentum, we've got two neutrino states. This one and that one. And that's because they can rotate into the electron. Notice I'm insisting on this linear combination because it's the one that we know exists because it has to because of the rotation from the electron field. And so that's two states. So, but on the other hand, there are three flavors. We could do the same thing for muons and tors. So we'd altogether have 6 neutrino states. So there are at least 6 nu bar, whatever, states. Now, of course, there could be more. It could be that there are right-handed neutrinos. Equivalently, we could be saying that not only do we have A1 minus, yeah, all right. In other words, we could have right-handed neutrinos, and in that case, we would have a plus sign here, a minus sign there, and a plus sign here. And similarly here, we flip those two signs. And then we'd have another 6 states. So these are left, and these are right. And so we don't know. There may be 12 states. There are 12 states for the electron, for the charged leptons. There may be 12 states for the neutrinos. And from the point of view of thinking about things, the simplest thing is to say there are right-handed neutrinos, and there are altogether 12 states. That makes it much easier to visualize what's going on. On the other hand, everything has to be settled by experiment, and experiments are going on to determine what sort of neutrinos we have. When I say there are 6 states, there are also 2 possibilities. The 6 states could be grouped into 3 Dirac neutrinos or 6 Majorana neutrinos. So it's things are up in the air. One way of telling the Majorana, whether these particles, whether these light neutrinos are Majorana or Dirac, is by doing neutrinoless double beta decay. And so, in other words, normally what you have when you have beta decay is you have a d quark go into an up quark plus a W minus, and the W minus decays into, for example, electron plus anti-electron neutrino. Okay. And on the other hand, if these things were Majorana, then we wouldn't really call that an antineutrino, it'd just be an electron neutrino. And then this guy could do the following. You could have nu E plus another d quark go into another u quark plus another electron. And this would be and that would be it. So the final state would be that this guy would go over there and create the second, do the second double. So let me just do that. So it would be it would stimulate the second beta decay, and in the final state, in other words, you would have something, some nucleus N, let us say Z, charge Z, go into a nucleus of charge, I guess it's Z plus 2, because we're generating 2 electrons, plus 2 electrons. And so you'd see something like this happen. Okay, people have looked for it, and most people in the field would say that it hasn't been seen at unambiguously. There's a guy somewhere in Germany who claims to have seen it, but most people don't believe him. On the other hand, most people didn't believe the man who told us that the solar neutrinos were oscillating. And until we realized, duh, he was right. So the guy in Germany could be right. There are more experiments being done. This is one of the most important questions in neutrino physics. Are these light neutrinos Majorana or Dirac? Yes.
this process only happens for Majorana neutrino.
Yes.
And for the reasoning?
Well, it's that what we have is here. Let me write it again. D goes to U plus E minus plus nu E, and but this nu E doesn't come shooting out of the nucleus. Instead, this nu E comes down here and becomes nu E plus another D goes to another U plus another E minus. So the total process is 2D goes to 2U plus 2E minus with an intermediate state that was, so let me maybe write the intermediate state. The intermediate state would be D plus U plus E minus plus nu E, and this then goes to 2U plus 2E. So in other words, in other words, if this were an antineutrino, you can't have, if it were Dirac, then you couldn't have antineutrino plus D doesn't give you this.
Oh, the neutrino in the first line has electron number minus.
It would have lepton number minus 1.
Okay. Oh, I see.
Okay, that's another way of saying it. Okay, so that's one of the really important experimental questions, and with luck, the Chinese will tell us what the answer is. I think in view of present Congress, there's no chance of our learning about it from an American experiment. All right. So if there are right-handed neutrinos, then we have two kinds of well, we can just make a Dirac mass term for the left and right-handed neutrinos, and we can have a Majorana mass term for the right-handed neutrinos. And it's also possible that it's possibly even natural that the Majorana mass term for the right-handed neutrinos is big, and if it's big, then we wind up with a mass matrix that looks a little bit like this. And you can see, if you diagonalize that, the eigenvalues are minus m squared. The product of the eigenvalues are minus m squared, and the actual eigenvalues then are, let's see, did I write this down at all? Yes, I did. Good. The actual eigenvalues are mu plus or minus is big M plus or minus the square root of big M squared plus 4 little m squared over 2. And you can see with the plus sign, big M, with the minus sign, a very small mass, minus m squared over big M. And so so it's kind of natural to do this. This is called the seesaw mechanism. This is the seesaw mechanism for one flavor, but of course in general this would be a 6 by 6 flavor. Since we don't have any experimental guidance, this was originally proposed, at least in the published literature, it's Gelman, Ramond, and Slansky. Jerry Stevenson was in the room, but he didn't sign the paper for some reason. Anyway. Now, the way in which we get information successfully get information so far about these neutrinos is through these neutrino oscillation experiments. And of course, the first one was done in the US when Congress actually funded science, and there was this guy in the underground mine. Well, most mines are underground. And well, you didn't get a candy. Here, let me give you a candy. So in the mine with the chlorine, carbon tetrachloride, that was the first neutrino oscillation experiment. And what happens, as I said to you before, is that these neutrinos go along as e to the I px. So this is e to the I p dot x minus I et. And of course, E is somewhat different. In other words, it's square root of p squared plus m nu squared. And if you work out what the phase is, if we say that the momentum of the particles are the same, so that the p dot x term is the same for all of the neutrinos, then the ET term can be different, and the change in phase is T del E. I said this last time, but we were running out of time, and you can rewrite this as L E over P, because P over E is this velocity, and delta E, and so this is L E over P, and it's square root of P squared plus M1 squared minus square root of P squared plus M2 squared. And if you expand these things, you see that delta phi is LE over P squared delta M squared, or L delta M squared over E. And you will ask me, I'm a little puzzled about that last bit, how I flipped. Well, I'm taking, these are relativistic, neutrinos are always relativistic, unless you're a very low energy, so P squared is E squared and stuff. So, let me tell you what the current experimental limits are. Delta M squared 2, 1. What we know then are that from various experiments, the original ones were on solar neutrinos. These were NeV type neutrinos. And people thought for a long while that was all that was going on. Then some people were doing experiments in which they were sensitive to neutrinos coming from the upper atmosphere or just coming right through the Earth. Well, also again, it's often from the atmosphere. And these were neutrinos in the KeV region, or I should say the GeV region. What am I saying? These were GeV neutrinos, and so eventually they realized that there were 3 mass eigenstates. Well, of course, when you think that we have 3 flavors of neutrinos, you expect 3 mass eigenstates. And so what one has is then M2 squared minus M1 squared, and this is 7.53. That's a 7, okay. Plus or minus 0.18 times 10 to the minus 5 eV squared. So 2 of these masses are very close together. And then we have delta m squared 3, 2. This is, say, m 3 squared minus m 2 squared. And this one, there are two choices for this. You see, when you analyze these experiments, you don't really know what the hierarchy is, what the mass hierarchy is. In other words, the natural thing is to say that that M1, the lowest one, that this is mostly type E, this is mostly type U, this is mostly type tau. And then these two would be very close together, and then this one would be up there. But on the other hand, you could have, it could be that 2 and 3 are close, well, no, 2 and 3 by definition are far apart in mass. But what the association, the flavor association is uncertain. And so this is called the normal mass hierarchy. And then the other case is delta m squared 3, 2 equals same thing. And in this case, it's 2.52 plus or minus 0.07 times, again, 10 to the minus 3 eV squared. So this is inverted. So one of the big questions is, what's the story? Is it normal or is it inverted? One handle on this can come from examining the decay of tritium. Tritium, as you know, is an H, which is NNP. So it's, what am I saying? Yeah, H is NNP. 2 neutrons in the proton. And I'm tempted to make a joke because there's probably more tritium in the Albuquerque area than any other place, or in almost any other place. Just for the record, we should get rid of nuclear weapons. Not just the ones in the Mideast, but the really dangerous nuclear weapons, the one in the United States and the one in Russia. Because there's an enormous number of nuclear weapons, and if somebody screws up, you'd have hundreds of millions of deaths. So if something goes wrong in the Mideast, by comparison, it's ignorable. But, and this is something that we were seriously worried about back when Reagan was president. And it's ironic, actually, because he was actually seriously trying to do something about the problem. And he and H.W. Bush did make some progress when, with Gorbachev, and got some arms control agreement. We also had a functioning Congress with 2 senators, Nunn and Lugar. Lugar was a Republican senator from Indiana, and he was quite reasonable, quite distinguished. And of course, in the primary, he was outed by some far right nut who said things to placate the extreme right wing Republican voters in Indiana, and so Lugar was defeated. And so people think that just because Reagan is no longer president, we don't have to worry about nuclear weapons, but in fact, it's a terrible problem. And we've just, people in California are more concerned with, more afraid of vaccines than of nuclear weapons. It's just completely insane. Okay, anyway, if you look at tritium beta decay very, very carefully, you can see that at the end point of, it's called the end point, it's where the energy, what shall I say? I guess it's where the energy of the neutrino is minimal and the energy of the electron is maximal. If you look at that region carefully, experimentally, you should be able to measure what the neutrino mass is. And because you know the total energy that's released, you know you can measure the energy of the electron, and so what's left is the neutrino that is moving at speed 0 and it just has its mass. So you have to do things incredibly carefully and accurately. There is, however, as far as I know, an experiment that has started or is funded or has been proposed. If it's not funded, forget it. But in any event, the Chinese will eventually tell us what the answer to this is. So what we would find out from that, of course, is whether the lightest neutrino is the electron neutrino, or whether it's tau or mu mostly, or whatever. Okay, so much for that.
So I'm sorry, what's the difference between normal and inverted? Is it? I don't know that.
Well, to tell you the truth, I actually didn't think of looking that up this afternoon, and so I don't quite know either. I can think of one difference is that you've got two states here and one up there. Another possibility is one mass state here and two up there.
Okay.
I think that's the difference.
Okay.
Okay. Lei Ma is an expert on neutrinos. And,
so the mixing that goes in M1 and M2 and M3, those are experimental numbers that we don't quite know yet?
Yes, and I should have looked them up. Okay, Thursday I will give you what the best numbers are for these things. Okay, I think you nodded also. All right, so let's see. I'm as I said, I had things a little bit disorganized. Yeah, but let me. All right, in view of the hour, let me go to the thing that's really crystal clear and simple. And in fact, that's what I tried to do. I tried to find things about the weak interactions that are simple, because after all, we have this action, we have this covariant derivative. Let's get the simplest physics out of it, rather than, as Schwartz does, the most complicated possible physics. And I looked in various books, nothing simple. I mean, you'd think somebody would just do beta decay or something simple. And so what I remembered was something that I learned from Sidney Coleman when I was a first-year graduate student. This was back in the 60s. It might have been 63. If not, it was 64. All right, let's think about the decay of the charged pion. So here's what we have. The pi plus goes into a mu plus a new mu. And this is 99.99 in round numbers % of the time. And you'd say, fine. Until you think a little bit and you say, well, wait a minute. What about E plus nu E? Well, let's see. What is that? That is 1.2 times 10 to the minus 4. That's the branching ratio. And now you look at phase space. This particle here, the pion, is 139 MeV. This one is essentially 105 MeV. This is 0.5 MeV. So the phase space here is humongous. It's almost 0 up there. So what's going on? Well, it's all because of that covariant derivative. Namely, this has to go through a W, so what actually happens is that the pi plus is u d bar, and this goes to d bar, the u goes into let me try to get this straight. Oh yeah, it's this thing all, sorry, it's much simpler than this. It's ud bar goes to a w plus, and then the w plus can go into u plus plus nu mu, e plus plus nu e. And you might say, what about tau? Well, the tau is much, much too heavy. It's what, a GeV or something. And the pion is only 140 or so. So what's going on here? Well, it's actually very easy to understand. First of all, the pion has zero angular momentum. And so when these guys decay, what we can have is this. We can have, mu plus, and then nu mu. Well, in the final state, we can have J like this, and J like that, and we can have, well, we've got to have P like this, and P like this, because the thing is, if we're in the rest frame of the pion, momentum zero, angular momentum zero. Notice one of the nice things about this is that well, all right. Let's just say that we've got the angular momentum and the momentum zero, but now what's going on? Well, this is a nu mu, and you see it's right-handed. Okay, so this is completely impossible. So, no. All right. The other possibility is that the J of the outgoing particles look like this. Now, the nu mu is right-handed, is left-handed, so that's okay. But now, mu plus is left-handed, but it's an antiparticle, so it should be right-handed. But it's not relativistic. Well, no, it's not relativistic, because the amount of energy here is like 34 MeV. The thing weighs 100 MeV. So it wants to be left-handed, it wants to be right-handed, but it doesn't really have to be because it's got such a large mass. So this thing is okay. It's not great. I mean, it would prefer to be the other way. It would prefer to be right-handed, but it can live left-handed. Okay, now we go to the electron. Well, the electron here is relativistic. The neutrino is relativistic. So if we do the same analysis here, we get no, and then we get no. Okay, but because the neutrino mass isn't, the electron mass is half an MeV, we do get a tiny branching ratio, 10 to the minus 4. So that's a nice explanation, I think, of some of the remarkable features of what am I trying to say? Pion decay. Okay, let's see. All right, one more topic. And this is somewhat technical. Here I'm following Schwartz. And let me give you the bottom line at first, skipping all the technicalities, because the technicalities, well, he skips 90% of the technicalities, and 10% that he does do are pretty complicated. So let me just say that suppose we're talking about this process. W plus Z goes to W plus Z. Well, now this is not something you're going to measure anytime soon, because good luck getting a beam of Z zeros. I mean, you could do it, but this is purely theoretical. Let me just say that if we actually, we can think about these massive particles as being, let's consider them all mass eigenstates, then they have three possible polarizations. So we can imagine producing beams of these that are polarized, so that all of these are longitudinally polarized. Instead of transverse, longitudinal. And Schwartz gives us approximate formulas for the polarization vectors. And then he considers one process. So this is WZ and WZ, and W has to go across, otherwise you wouldn't have any charge. And he works that out, and let me just say that, let me just give you the bottom line. The bottom line here is, well, actually it's kind of complicated. All right, you get, this is the S channel amplitude. There's a U channel amplitude, which is and we have this guy going across like this, and this one going under like that. And so we have, so this is called MU. And then, of course, there's the simplest case, which is called M4, which is just this. Because there's a four gauge boson vertex. Okay. If you add them up, you get MS plus MU plus M4 is approximately T over V squared. V is this 246 GeV, and T is the Mandelstam variable, P1 minus P3 squared. And let me label these ones. P1, P3. So those are the two that we're talking about, the two W's. Okay, well, here's the problem with that. As you bring up the energy of these beams, V squared is a constant, T is going to get bigger and bigger and bigger, and so you're going to have a violation of unitarity. Remember, there are the unitarity bounds that I went through last time, which follow from the S matrix being unitary. So these total cross sections can't be too big. And all right, well, what comes to the rescue here is the Higgs. Namely, there's one more term, MH. And what does this look like? Well, this is W coming in. A Higgs going across. And the Z's doing that. And what is this amplitude? Minus T over V squared. Plus smaller terms. So in other words, the Higgs cancels the growing amplitude from the gauge boson terms if you leave out the Higgs. And this even provided people with a bound on how big the Higgs could be, how massive it could be before it was discovered. Because what they realized was that if the Higgs was too massive, then you wouldn't, this term wouldn't play a role until you were at very high energies, high enough for the Higgs to, because you see this Higgs term here, this thing is going to be, it's a T minus mass of the Higgs squared. There are it's roughly that cubed, right. So there's mass of the Higgs to the power 6 in the denominator of this thing, which combining with a lot of other things gives you that. And so people realize then that you get a violation of unitarity until you cranked up the energy high enough for the Higgs to show up. And the people who published that were Lee, Quigg, and Thacker. And what they showed was that the mass of the Higgs had to be less than or equal to something like 16 pi over 3, 1 over v, which is in the order of 1 TeV. So their upper bound was high by a factor of 10, or maybe 7, say, or 8, but still it was a ballpark estimate. Lee, unfortunately, was killed in a traffic accident. So, by the way, was Sakurai. And I think also Landau. Yeah, so my youngest son went to work at Schlumberger, and one of the things Schlumberger is oil services, so you have these very dangerous, very, maybe you should turn the camera around. Actually, I'm a little worried that you've been playing with your tablet. Have you paid any attention to where I was during?
No mistake.
All right, well, let's hope it was aimed at the equations. Anyway, so the first thing they do with Schlumberger people is they teach them how to drive safely, because the most serious cause of injury and death in the corporation is traffic accidents. And because the drilling rigs, of course, are not typically in the center of town where people live, people have to do a lot of driving, and so so it's important to deal with it. But it's really remarkable that when you have the sort of equipment, with corrosive chemicals, radioactive materials, high pressure hoses, and we're talking high pressure sense that just extraordinary on drilling rigs. Let's see, we do have a couple of minutes left, and somehow I thought that I had prepared far too many things, but I seem to have somehow gotten through. I guess because I skipped a lot of stuff here. Let me just write down these numbers, these quantum numbers for the standard model. And what we have are, we're just looking at one generation. So we have U left, down left, U right, down right, lepton left, which is nu left, E left, and then we have ER. Now these quantum numbers, I think, are really nuts. First of all, let us say T3, and here it's plus or minus a half, 0, 0, plus or minus a half, 0. And then we have y, 1/6, 2/3, minus a third, and minus a half, and minus 1. Well, boy, there's a lack of symmetry there. They are just really ugly numbers. And I guess we should put in the Higgs since it exists. So what is the Higgs? Well, it has T3 is plus or minus a half, and this one is, I think it's 1, isn't it? Yeah. Then we have an H plus and an H 0. So this suggests that, you know, somehow there's some way of extending the standard model, and the view back in the 70s, when most of this was known, was that, well, of course, we also have the strong interactions, and so we have this is just number. Well, I don't know what number, but these are color triplets, of course, and then 0, 0, 0. So the idea was, well, in order to have a nice theory that's somehow symmetrical, we need to go to very high energies and unify the strong with the electroweak interactions. And the idea here is that, of course, with running coupling constant, you have alpha for the strong interactions going down, and you have the weak going down quickly, and then the electroweak coupling goes more slowly, and so maybe they meet. Well, they don't quite meet, but if you add supersymmetry, they meet. But again, even running this far assumes that nothing happens in this enormous range. And if you add supersymmetry, well, now what does that mean? Supersymmetry means double the number of fields. You just bloody well double them. So it's like the opposite of Occam's razor. You want to explain something with the simplest possible explanation? No. This is the most complicated possible explanation. And moreover, when you have these supersymmetric theories, I think you have at least 100 free parameters, which is why the champions of supersymmetry have been so happy for the last 50 years. All the experimental evidence has been against them, but they've got 100 parameters to adjust. And as Victor once said, give me 5 parameters and I can create a curve that draws an elephant. Yeah. Well, I shouldn't make fun of this because it could be, you know, this is what we're in April. By next fall, they may have discovered SUSY particles at the LHC, so I could be proven wrong. But it is certainly not a simple explanation. Anyway, since the discovery, though, of supersymmetry, people have taken dark matter seriously. The observations on dark matter have become more compelling, and people realize that there's 5 times as much dark matter as ordinary matter. So it could be that the way in which you make this far more symmetrical is to introduce other fields at ordinary energies that are the dark matter particles, some of which are the dark matter particles. And the natural thing to do, if you just want to stay at lower energies, is to say, well, these guys really are a doublet. Or if these guys aren't a doublet, well, here I'm doing what the supersymmetry guys do. You can double all of the ordinary fields and say that they're dark fields. But then the dark fields, instead of having left-handed particles interact, they have right-handed particles that interact. Well, I don't know. Anyway, there's a lot of mystery out there that we need to somehow understand with a lot of new experiments and new theories. We can't expect Congress to fund any of that, but we can hope that the Chinese will tell us what the answer is, and that somebody will translate their results from Mandarin into English. Maybe Lei Ma and, how do you pronounce your name?
Jixian.
Jixian.
Jixian. Yeah. It's hard.
I've tried 20 times. I can't
Too
get
hard.
anywhere near it. We'll translate the major results for us. All right, so that's it. We can